In the race to build smarter and more powerful AI, we're always thinking bigger is better. More data, bigger models, more compute. But what if the biggest breakthrough comes not from adding more stuff, but from adding one simple rule? A single guardrail that tames the chaos and unlocks stable, incredible power. Well, let's get into it. Okay, so what you're looking at here are three different ways to design the information highway inside an AI's brain. On the left, you've got the classic, tried and true method that's been the standard for a decade. In the middle, an ambitious, new superhighway. And on the right, that's the hero of our story today. So what's the big difference here, and why did that superhighway in the middle fail so badly? To really get why the new design is such a game changer, we first have to understand the road it's built on, the reliable but kinda limited foundation of almost all modern AI. For well over a decade, deep learning has had this secret weapon called a residual connection. The best way to think about it is like a single, dependable lane on a highway. It's a straight shot that makes sure the information from the very beginning of the network doesn't get lost or garbled by the time it gets to the end. It's simple, it's super stable, and it just works. But, a single lane road can only get you so far. What if you want to go faster, carry more traffic? That's exactly where this new idea, called hyperconnections, or HC, came into the picture. The whole point was to tear up that single lane road and build a massive, multi-lane superhighway in its place, hoping to unlock a ton more power.
And we're not talking about just a small tweak here. This was a ground-up redesign of that core information highway.
So here's how hyperconnections work. First, they split that one lane of information into a whole bunch of parallel streams. Then, and this is the clever bit, they add these smart traffic controllers. In math terms, they're matrices, but you can just think of them as little AI agents that learn how to best mix and merge the information flowing through all those new lanes. The really amazing part was the goal, to massively boost the network's power without a huge jump in the raw processing costs. And this was a huge deal. It promised a totally new way to make AI better. I mean, instead of the old playbook of just make the model bigger or throw more data at it, you could now make the architecture itself richer and more powerful. It was like discovering a whole new dimension for improvement. But there was a serious problem hiding under the surface. Because it turns out, when you build a superhighway with no speed limits, no lane markings, and no guardrails, you get something that feels like a high-speed wobble. And in the world of AI, that wobble leads to a spectacular, catastrophic crash. Okay, so here's the critical flaw. By creating the super flexible, unregulated highway, hyperconnections accidentally threw out a golden rule from the original design. It's called identity mapping, which is just a fancy way of saying make sure the signal can pass through unchanged. Without that basic rule, the information traveling down the highway could either get amplified into screaming feedback or just fade away into nothing. And this is what that looks like in practice. Just look at this training graph. The red line is the hyperconnection model. It's learning, it's doing fine, everything seems great, and then, bam. Right around 12,000 steps, it just completely falls apart. That huge spike means the model's performance has utterly collapsed. If you're spending millions of dollars on a training run, that right there is an absolute nightmare. And this chart shows us exactly why it failed so hard. This is measuring how much the signal is getting amplified. Look at that dark blue bar. That's a signal that has exploded to 3,000 times its original strength. That is the speed wobble. That is the out-of-control feedback loop that sends the entire system spinning into chaos. So it all comes back to this one core idea, identity mapping. You can think of it as a law of conservation for information. It's a guarantee that a signal can travel through layer after layer without getting totally mangled. By getting rid of this, hyperconnections basically open the floodgates to chaos. So, the big question is, how do you get all the power of that superhighway without the fiery crashes? Well, the answer turned out to be surprisingly simple and honestly beautiful. So let me introduce you to the hero of the day, manifold constrained hyperconnections, or just MHC for short. It's a brilliant idea. You keep the multi-lane superhighway, but you add back one simple, powerful rule, a mathematical guardrail. Now, that guardrail is called a doubly stochastic constraint. I know, it's a mouthful, but don't worry about the name. What it does is simple. It forces those little traffic controller AIs to behave. It lets them mix and blend the information perfectly, but it prevents them from creating or destroying energy. The total signal is conserved. It's like installing a flawless traffic management system that makes pileups impossible. And this one simple rule gives you three incredible benefits. First, norm preservation. That just means no more signal explosions. It's solved. Second, compositional closure. It stays stable even if you make the network 1,000 layers deep. And third, it actually turns out to be the perfect way to fuse information from all the different streams. You get all the power and none of the chaos. And you don't even have to be a math whiz to see the difference. Just look at this. On the left, that's the traffic controller from the old unstable model. It's a chaotic mess. On the right, that's the new constrained one. It's clean, it's orderly, all the energy is focused right where it needs to be. It's literally a picture of chaos versus control. Okay, so the theory is elegant, the pictures are convincing, but does it actually work in the real world? Let's look at the numbers. Remember that catastrophic failure spike from before? Well, check this out. The new MHIC model is the solid blue line. It is perfectly smooth. No spike, zero instability. And it's not just stable, it's actually better, consistently outperforming the original single-lane design. And here's the smoking gun. Remember how the signal was exploding by 3,000 times? With the new guardrail in place, the maximum amplification is capped at just 1.6x. That is a reduction of literally 3 orders of magnitude. The speed wobble is gone. The highway is finally safe to drive on. All that stability translates directly into better performance. Look at these results. On really tough benchmarks for reasoning and general knowledge, our new MHC model in that last column is the clear winner every single time. It beats the original design and it crushes the old unstable one. And the gains in reasoning are especially big, which is exactly what we want to see. And this isn't some trick that only works on small toy models. This chart shows that as you scale up, making the models bigger and more expensive, the performance advantage of MHC just keeps on going. This proves it's a real, scalable solution that's ready for the next generation of giant AI models. Now, you're probably thinking, okay, this is amazing, but it must be super slow, right? Well, here's the kicker. Thanks to some really slick engineering, all of these benefits, the stability, the better performance, it all comes at a cost of just a tiny 6.7% increase in training time. That's an incredible bargain. Which really just leaves us with this one last thought. This massive leap forward came from taking a powerful, ambitious idea and adding one simple, elegant constraint back in. It really makes you wonder, in our mad dash to build bigger and bigger AI, what other simple, fundamental rules of the road have we left behind? What other elegant guardrails are just sitting there waiting to be discovered?